present this seminar in the series that you have on teaching and learning from Griffith University, out of Griffith University. I'd like to go to my PowerPoint presentation now, if I may. Let my technician look after me. Okay. It's a very packed presentation. It's about half a gig big because it does contain video material, which I believe has a big advantage over just written down material, but we can't not avoid the words either. So bear with us whilst we get some action going here. We might have to restart the presentation.
Well, it's fine. We have time. We can wait for a little bit, right?
Yeah, yeah. Well, I've got the rest of my life. I don't know about anyone else, but I've got plenty of time. My doctor says I'd be lucky if I was to live another 30 years. But I said, oh, no, luck's got nothing to do with it. You've got to look after yourself, take preventative medicine, a glass of good red wine with a meal is a good way of achieving that.
Really? This is a really good exercise, really good
advice.
medicine.
Yeah. Bear with us. We didn't have this problem obviously earlier, so it just reared its, dare I say it, ugly face now. But we'll soon be going, I'm confident. But yeah, look, whilst we're taking up a minute or two, I'll tell you what's on the first slide. Basically, it tells you that I'm involved with 4 different organisations. Swinburne University of Technology, the University of Melbourne, where I was for about 40 years prior to my retirement in 2010. I still have an association with the University of Melbourne, and it's a close one, obviously, having been there for so long. I'm also heavily involved with a company that I started 25 years ago called STRUCOM, Structural Company, that's what it stands for, the acronym, which does a lot of consulting to industry and the government. But also in the last few years post my retirement, inverted commas, has been producing teaching equipment under the trademark TechnoLab. This teaching equipment is meant to be a swing back to hands-on opportunities for students to learn basic structures from statics, mechanics, and into dynamics. So across the board, from early years to much later, postgraduate even, a master's and higher degree students who need to go more in depth. But the biggest feature of this equipment is it's been designed basically from scratch. I've used equipment in the past that's hands-on and has got a physical presence in a room. That seems to have disappeared from most of our universities. And that's why I've worked in that field. So today I'm representing Swinburne University and TechnoLab, the trademarked products, teaching products. So we're up and going. Okay, I'm going to concentrate on the Swinburne University of Technology delivery of subject Eng 2003, Mechanics of Structures. This is a first year subject that's dealt with in first and in second semester for all of the engineering students. The 2 semester cohorts are significantly different in size, about 100 or under for first semester, and about 300 or more in second semester. So it's disproportionate. Sorry?
Nick, can you click on the screen? There is like some window, it says live captions, subtitles. Can you just click got it so that we don't see it? I mean, if you go,
I
yeah.
don't see it.
You
I don't see
it.
that in my delivery. So
Strange, because it's kind of on the like half of the slide. If you go a little bit down, then it just.
Yeah, my technologist will take care of that, I hope. He says there's a got it. You have to press
there
this
is like
icon.
some kind of window that if you
A
click,
window that you
so
have to click to close.
Because I can see it on my screen and it blocks half of the PowerPoint slides. So I thought.
Oh, I see.
I mean,
Yeah,
not
we're
half.
looking
Half
at,
the PowerPoint slides. Apparently.
we're looking at presenter view currently.
Sorry, what was that?
We're looking at presenter view.
Okay.
Yeah, maybe if you can just go with like full presentation, not.
Yeah. Let's see.
Maybe click that from beginning. Can you click from beginning or from current slide, the presentation, so that it's.
Let's go slideshow and then.
Oh,
it normally-
slideshow. And that from beginning, the one on the left hand side on the top menu. No, can you click that one? Okay.
Yeah.
Yeah, I think this is yeah.
You see that okay? Like
Yeah,
full screen, or is
yeah.
that a
Full screen now. Full screen now. Yes.
awesome? There we go.
Okay. Yeah.
Thank you. Sorry for those glitches, but we're trying to do a lot more than just a plain PowerPoint presentation. Okay, so some references, only a couple here. If you want to know more about the experience at Swinburne University of Technology, there's a publication from the World Engineers Convention back in 2019, and that's just prior to the COVID-19 rearing its face worldwide. And more recently, there's a paper, but it's under review, on the experience again at Swinburne University of Technology in teaching this first year mechanics subject. So you can expand upon what I'm presenting today if you wish to. So in summary, some of the features I think I should note early in the piece, in case the technology may let us down again, I don't know. But I'd like to make sure that we've got these take-home points. There were 2 Technolab experiments that Swinburne University chose for its experiential hands-on learning. And they chose 2 major topics, which I'll expand upon shortly. And these major topics students had trouble with, they grappled with in the past. And so they used these experiments formally for report writing and also for subject assessment purposes. So the actual hands-on experimental component in this Eng 10003 course only involved those 2 experiments. Once COVID-19 came on board, these 2 Technolab experiments weren't able to be done hands-on, except for one occasion, which I'll refer to later. We're not able to be done hands-on by the students. So we video photographed the full performance of the experiment involved, both experiments involved, and these were presented, and the results or observations presented to the students. They then wrote up a report based upon their assessment of the information and analysis of it, and also their own independent analysis using modeling techniques. Well, from the 2019 and also 2020 experience, we found that students were more keen on doing hands-on experimental style physical experiments, especially after the lockdown period. And this led to Swinburne deciding to use some additional, albeit smaller, topics that were hands-on experiment that involved hands-on experimentation and captured by video and photography. And then these were delivered in the 2021 and in the first semester, and is going to be delivered this semester, or is being delivered this semester. One feature of the lockdown in Melbourne, Victoria in particular, was during the 2021, the first semester, there was an opportunity, a small window of opportunity to do some hands-on activities by the students. And this primarily on one of the two experiments, the bigger experiments that they had to write a report on and be assessed on, but also gave them an opportunity to actually visit the experiment test rigs that they saw on video in their deliveries, in the online delivery. Okay, so two experiments, what were they? One was the T3 experiment from Technolab, the 7-bar Warren Truss. The other was shear force and bending moment in a simply supported beam. They were the only two performances I set up to date, but with post or into the COVID period, they were able to see video clips of additional experiments, and they were lucky to have an opportunity on two open sessions to visit these for themselves. Okay, here's experiment T3. What does it look like? It's a 7-bar truss. You see the members can elongate and contract. They are sprung members. You can see that there's a roller there and a simple support on the left. And for this case, it's two loads simultaneously being applied. The students look at each of the loads separately and the response of the structure, its reactions and its internal member forces, and then they can use superposition to verify that, hey, you know, the results for a single load, each of the single loads when added together, provide you with a result that you should get for when both loads are applied. The other experiment is the shear force and bending moment experiment, which involves a specimen with a splice. The splice portion can be removed to produce one or to allow you to investigate one of the two segments for equilibrium, to give you the same reaction and shape of bending by applying a moment and a support reaction at the end of the segment. And this enables you to get shear force and bending moment. Well, like I said, during 2020, we had severe lockdowns. This shows you the COVID daily cases and also shows you the two semesters in each of the 2 years, 2020 and 2021. I'll show on top of that, we don't know what's going to happen in the near future. Different road paths are suggested for us, but golly, we really don't know. There was an all-out effort in the first year to try and get everything online by most universities, including Swinburne. Material had to be filmed, photographed, videographed, made into a form that could be presented online and engage students. Well, after the first of the 2 years, we had our student learning assessment survey results at the end of the second semester, which is the biggest cohort, suggest that we need to see more experiments. We'd like more hands-on. We don't like online, as you'll see a little later. Well, into 2021, we had an opportunity to have an open lab with Technolab equipment that students could visit and play with. These were largely drawn from the experiments that were presented to them online, the additional experiments that were presented to them online. We also had all the students able to do the hands-on. Now, this being the smaller cohort of students, the small time window that we had of about 5 weeks enabled us to do these things. We had a second open lab to cater for the remaining videos that were shown of experiments hands-on a little later, about a month later to the first one. So there were these 3 opportunities that students were able to visit hands-on. Okay, what did the semester 2 2020 suggest. We had standard 6 questions in the student learning assessment survey, and for the subject versus the university versus the faculty, you can see the standard 6, there was 7.7, which is below but equal to the faculty result for the subject, but the rest of the faculty seemed to get higher. Sorry, the rest of the university seemed to go higher. An additional question was introduced in the SLAS, and that shows a clear 1 point or more below the standard 6. I found online learning an effective way to study this unit. Most students didn't agree. Well, it's still a high score, I suppose, but it's well below the standard 6 questions that you have on SLAS surveys. And the thing is here, the subject itself was lower than the mean of the faculty and the mean of the university. Okay, well, the 5 experiments were introduced in photograph, videograph form. These ones shown pictorially here. We'll go more into them. So on top of the T3 and F8 experiment, on which they reported and were assessed on, primarily towards their final assessment, there were these additional clips. I'll go through the 7-bar truss experiment, the video of it, to show you basically how or the presentation of it, PowerPoint presentation of it, so you can see what is involved. Here's our 7-bar truss. It's unloaded, so we can get the initial conditions. Okay, so you can see that there's a rod that goes through the bottom of the frame and onto the scales. So you can take an initial reading of the system for its reactions at the base before you apply any loads. And these are the readings. We try and, although it's not perfect here, we try and capture in the video, so you know that these numbers are the same as what you were shown in the photographs. So photographs are taken as you saw, and you can see those photographs being taken. You can read virtually what's on them reasonably well, and so you're reassured that everything is bona fide. It's not concocted. Nothing's done maybe sleight of hand. Okay, what then? We apply a load, but I should say that we also need to get the initial position of pointers inside the slots that you can see of each of the members, because that gives you an idea of the position of the internal sprung system. So these are done. You take photographs of each. And this is what you do. You find out the relative position of the pointer in the slot for each member relative to the length of the slot in photograph units. Now that proportion is the proportion in real units of what the position would be. And so if you know that real length, which is 13 millimeters, you just multiply the ratio of 102.2 on 191.3, in this case 0.534, multiply that by 13, and it will tell you where the pointer lies in that member in millimeters. And you can do this for all members, and you will get a different number depending upon the position under those initial conditions. And here are the summary of the results for each of the members. You then do it with a load. Here's what we do. We apply 0 our scales. We take a measurement of the load. We take a photograph of that so we know what load is being applied. In this case, it's going to be applied centrally. It's then applied. And you can see already that certain members elongate and others contract. You just make sure that there's no friction or stiction around by just moving up and down. And then you can record the reactions. And again, you can barely read it there, but you may be able to see it. But those photographs will be shown afterwards, and that's where they are there. And so, yes, it's about 194 gram or about 1.9 Newton of force being applied centrally. And they're the two readings of the support reactions. And you can do the calculations. And in this case, because it's less error involved in looking at working out ratios of position of pointer to length of open slot, you get very good accuracy. Look, it's almost spot on to 3 figures. It's near perfect. Okay, well, you go through and do the members as well. And yes, you take the photographs, you get the ratios, do it for all the members. And finally, you get the B on L ratios. And from those B on L ratios, you can find out what the extension or contraction is of each of the members. And because you know the spring stiffness, and in this case, although we have several different spring stiffnesses we can choose from, we do have a spring stiffness that is purposely designed to give us 1 Newton per millimeter of movement of the pointer, so you can get the force very accurately. And so this is what happens. Multiply the 13 millimeters by the change in B on L ratio and multiply by 1 Newton per millimeter, and you get the results for the internal member forces from that analysis. Okay, what about theoretical evaluation of forces? Well, you can use the method of joints, graphically or algebraically. You can use the method of sections, or what I do, just for fun, I like mathematics as well, matrix solution of the equilibrium equations for the truss as a whole. And I supply that with a Excel program. So here it is, here's our truss. We can set up simultaneous linear equations of equilibrium for each of the joints. There's 5 joints, so there'll be 10 useful equations of statics, and there are 10 unknown forces, 7 internal members, and the vertical and horizontal reaction at node 1, and the vertical reaction at node 5. We can set up a set of 10 simultaneous equations in 10 unknowns for the applied load, and yeah, we can get results. And there's the results. I've actually inverted. You don't. You can just solve the equations, but that's fine. They're the results from the analysis. They're the results from the experiment. And as you can see, there's about anything from up to about 10% error, or plus or minus 0.05 Newton, because of the stiction friction that can occur. We can't eliminate that entirely. Okay, so we got students to report on their assignments what they got out of experiment T3, and they gave a score out of 5, and it's okay, but overall, the one I'd like to draw your attention to is 4. They understood a lot better, having worked with a physical model, how a truss behaves. They also had an opportunity for other feedback, 64% of a class of close to 300, and I've just chosen a few here. This lab was pretty interesting, just took ages to complete, so they did a lot of practice, but helped me understand how to do the calculations a lot more, which was awesome. I'm just choosing a few, obviously the more favorable ones, but there are others there. In this class, I have a great understanding of the calculation of the carriage structure. And I also learned to use photography to measure data. Photogrammetry figures largely in a lot of Technolab experiments. Number 16, I'll just go to that. I do not think I gained anything from doing this, since I could not do the experiment on my own and have to rely on a video made by teachers only. However, it is understandable due to the current pandemic we are in. I think that sentiment, although not written down by many students, was shared by others as for this student. What about the other important experiment F8, which all students do and write up on and get assessed on? Unfortunately, the 4th line, which was other comments, somehow missed being on the assessment, on the table that students got with their pro forma for writing up their report. So unfortunately, we don't have individual comments, but what is surprising to me was that this was a more complex experiment to grapple with, but the students preferred to have done it compared to more worked examples. So in other words, if they were given the choice of doing the lab or going through more worked examples with their tutor or lecturer, they preferred doing the laboratory session, even though it was, in this case, videoed. Okay, let's look at those 3 opportunities that we had to do some hands-on. So we're not relying on the online now presentation of the captured videographed, photographed lab sessions. So we had student interviews available to us as a result of being able to intermingle with the students at those times, albeit with distance requirements of 1.5 metre separations. At that time, we didn't have mandatory masks, but we were able to do that. So there were 3 opportunities: open lab session 1, where students could use and have a play with any of the experiments that they were shown via video during that semester, although it was part into that semester. And also the Truss experiment, they were able to actually do, all students were able to do the Truss experiment because there was less than 100 of them that could all do it on the one day in a one hour session, one session after the other. And yes, we had a second open lab session about 2/3 almost, 2/3 into semester 1. Okay.
In 2020, what was the biggest challenge for learning engineering remotely?
Staying motivated. It was just getting up in the morning and having to do the work when you don't really have anywhere to go.
Yeah.
You've got to just sit there in the same place, and you really couldn't go anywhere, especially during the higher stages of lockdown. It was just really, like, it killed it. Like, I normally and really enjoy this stuff, but I was starting to hate it back then.
And that's mainly just from being virtual as well, like being from home.
And also because of the lockdown, I think it was the social isolation as well.
And the stress of it, I guess. So.
Yes. Oh, well, even just this morning in a couple of hours, and it's just having somebody talk to you and explain it with, like, your reaction to it, and being able to physically interact with this stuff as well. I feel like you just learn so much more in such a short amount of time. It just really, like, it gets into your head. That's what engineering is about. It's about actually doing stuff. And you can't. That's what you've got to actually do.
Yeah.
Learn how to do it. You got to have practice. You got to know what you're going to do. You don't just know about what you're going to do. You've got to actually get a feel for it too. And that's also, I guess, it would help you if you were wondering what field you wanted to go into.
And so you think if you had this hardware being used in your learning throughout, like, year 1, year 2, year 3, and so on, that would give you, like, a really strong basis?
A massive, yes.
Yeah, why is that?
Huge. Because it's just physically applying it. You remember it. You've learned it, and then you get to actually do it, and that's like another method of revision. But it's also like, if you have a question, you think, oh, what if I change this, or what if I do it differently? You can figure that out for yourself. It's like the scientific process.
No, that's a good analogy. Yeah,
that's a really good way to learn.
Okay, so that was an interview after Open Lab 1 session with one of the students who volunteered. And as you can see, you can hear as well, they don't particularly like the online. They'd rather have the hands-on opportunities. So let's now look at the Truss experiment, where the whole class was able to do hands-on experimentation of the Truss experiment in smaller groups, one after the other, 1 hour sessions on one day, this being the smaller class, less than 100 students.
Personally, I'm very much a visual learner, so when you see it on paper, sometimes it's a little bit hard to know, like, even tension and compression and stuff like that.
Especially being able to see the spring inside the actual members, that was pretty useful for learning, actually being able to see the reaction.
Yeah, no, sort of the online sort of videos to that allowed you to use a different part of your brain than you would when you're just doing the constant questions.
When we first started studying the Truss kind of subject in this unit, I thought it looked quite daunting. Like it actually, like especially through the textbook and the examples they give it. Sometimes you could look away for a second, you could easily get like lost by the examples. But like when you're actually like doing it and it's in front of you, it's a lot easier to follow kind of like where the force is being distributed.
I found the equipment that we were using very easy to analyze and study, and that was just really appealing to me.
To get the value out of the real thing rather than a diagram.
There was a lot more feedback, you know, visually, haptic, like I could see the trusses moving, I could get a way better idea of, you know, how it's moving, how it's working than compared to some maybe online simulation or, you know, written example.
Okay, I think that particular video, you could see that there was a dozen replicates of the experiment, the classroom bundle that students were able to use, and on their own, and with distancing requirements of 1.5 metre separation. No need for masks, that wasn't compulsory. You can see that you can deal with that in a typical practice class tutorial room, which might accommodate 24 students. Normally, that's what would happen at Swinburne, and students would normally work in pairs, and so there'll still be some group interaction, but no more than 2. 3 or more becomes a demonstration. It doesn't become true experiential learning. Now, the third opportunity was another open lab session of 2 hours where students could come and use the equipment. And so I have a short video on that as well. The sound is not coming up too well. Okay, I'm going to look at the 5 experiments here that had short videos of them put together. I'm not going to look at them all in any detail, just to list them. Simple equilibrium of forces at a point in 2D. It's one that most people who produce teaching equipment in this area would have available. Here's a version that I have. You can have a window behind that and record the orientation of the lines. And of course, you measure the weight forces. And you can solve by using vector algebra, or you can use algebraic, some of the forces horizontally and vertically equal 0 separately, to solve for one of the forces being unknown, and then compare with the actual force to show that it's the correct force. There's not lots of ways of dealing with this problem. But these 5 clips provide, oops, sorry, I went the wrong way. Here's an example of a 2-bar truss. Yes, you can get the force equilibrium, and you can show, well, in this case, approximately 5% error of observed versus theoretical results. We should have symmetry. We don't quite, but it's good enough. And the errors are less than 5% or approximately 5%. Experiment 2, 2D equilibrium of a rigid bar. You get reactions, and you can apply a moment at a point, or you can apply inclined forces or vertical forces on that rigid body. And you can also measure the horizontal reaction with that member on the right there. It's like a truss member, so you can get the internal member force of that. And the other 2 supports on rollers only have vertical reactions. So you can investigate that system experimentally and get very good results, very accurate results. Here's reactions of a simply supported beam due to a point load that you can position at different locations. Another one is 3-dimensional forces. We have truss-like members oriented at different orientations if we want to. A couple of that we've chosen is one that's symmetric, another one that all the members have the same length, so it's a tripod, if you like, with that is perfectly symmetric. You can apply a horizontal load, you can apply a load at an inclination. Simply supported beam, this time I'm looking at it as an experiment. What the kids might see is this video clip. You measure the load, it's 293 grams approximately. That was easy. Then we apply this load very close to the left support, and you can see 262 and 20 approximately gram. You can see the results on each of the vertical reactions. For each of the vertical reactions, as the load moves across, you can get its relative position to the ends, and you can show that as the force moves to the right reaction grows, the left reaction lessens. The sum of the 2 reactions is still equal to the applied load, or close enough to experimental error. Yeah, things are fine. This is taken from a photograph, the length 109, that length 31. You can do an analysis, and yes, you can get the results. And what do you know? They conform closely to the results that you obtain from measurement of the reactions. And yes, you're happy with what's going on. Excellent agreement. And similarly, for another point along the beam, again, the agreement is rather excellent for simple cases like this. Hands on? Why not arms on? This time you only see the one reaction on the left, and it's you don't need to photograph now because we've slanted the screen by breaking into the actual digital scales and transforming it into into one that's easier to look at for filming purposes. And we're doing away with a student. Who needs students when you can have a robot, eh? Is that what's going to happen to all of us? We're going to be all replaced by robots. We don't need to know things and be able to do things for ourselves. Oh, woe is me. What's going to happen to us? I don't know. But you can clearly see the reaction going down. And if you do the arithmetic from the ratio of positions from one end of where the load is to the span, you can show those results. But yeah, you can also have a bit of fun. Students like seeing this, and they can still get do the analysis and the results. But believe it or not, 50-50 of them. Others still like the person placing the load on there and then following what they're doing, as opposed to a mechanical system, a robotic system like this. Okay, some things from student feedback in semester 2. We looked at this earlier. We got 7.7, 7.82 and 7.7 for subject, university and faculty for 6 standard statements. These were revised for semester 1 to 2021. And the change that occurred here, well, first of all, they went up a bit, not a lot, but a bit. But the difference was that this subject fared better against faculty and better against university as a whole than it did at the end of semester 2 2020. And we put this down to the fact that we did introduce the additional online material that had video capture of experiments and also the small opportunity for them to do some hands-on as well. That's what we attributed it to, but you know, it's not obviously as convincing as it could be if those numbers were a bit higher. Concluding remarks. Well, enhancement of online delivery of statics, mechanics and dynamics using video photographic capture of TechLab experiments performed hands-on assist students' understanding of basic principles, concepts and analysis and modeling techniques. A lot better than, I would say, simulations or other methods. But the big thing is that students do value on-campus experience. They value the interaction with academics and fellow students and the opportunities to perform experiential learning using physical models that they can explore for themselves, such as what you can get from the TechnoLab series. So that's where I like to end my presentation and go back to the camera, if I may. Okay, I still see some names up on the board, so I didn't scare too many people away. Wow. Okay, well, here's an experiment that the students did that you can see. Can they still see me? Okay, good. I'm going to just go up here and slide my hand inside so you can still see something here. And I'm going to pull this down and you can see that the roller moves a bit. And if I pull it hard enough, the whole thing lifts up. And that's one of the reasons why there's a weight at this end. There's a weight there. It can be in the form of a vertical weight that has a rod that goes through the base to a reaction measuring device, a digital scales, or it could be disc weights like I have here. And that tells the student something too, that if you have sufficient overturning moment, you may lift off your reaction. So if you're relying on the self weight of the building, and it's not enough, you have to tie it down. So there's additional lessons that you can get. So that's that one. Let me move over now to this one here, and I'll get this out of the way. I think it looks better with something behind it that cuts out the background. Here's a different sort of truss. It's an 8-bar truss. Again, it's reasonably complicated, but it has those simple features of being able to measure the internal forces through the extension or contraction of the rods that can be measured, the internal rods of each of the members, because that can be measured using simple photogrammetric techniques. What I also want to show you here, pardon my hand, it's in the way a little bit, but if I move this up and down, you can see that the roller moves to the right when I push down, because the members, the bottom members are in tension. You can see that and I've taken it off now, that's okay. You can also see that these members, the corner members, hardly extended or contracted at all. In fact, they should be zero member forces because there's no applied load. But if I were to instead pull on here, sorry, I haven't got a weight that I can easily use. If I was to pull on here, you would see that the member forces on the node that is being pulled on will be non-zero, but the corner, the opposite corner, those members do not increase or decrease in their position. The node in the middle moves the same amount to the right as the node at the top left-hand corner. So that horizontal member does not go in tension or compression. Member 2 does not go in tension or compression. Member 4 does go in tension because I'm not applying the load in the opposite direction, only pulling down. So that's another sort of physical experiment that you can do, and you can play around. And that's the idea with the students. They love playing around with the equipment and seeing for themselves what can happen. So here we've got only a 2-bar truss, very simple. Why not have that as part of your, let me pull this back a little bit so you can see a bit more of it. Again, if I pull on this, you'll see the members elongate and contract. In this case, they will. There'll be more elongation on one than contraction in the other, and the pointer moves, etc. So you can get the internal member forces. You can arrange for the load to be, the pulley to be anywhere you like. So you can have an angle of application of the force to be different, and students can explore this in their own time. Okay, I see that I've got about only 5 or 6 minutes. We did start a bit late, but I think I've spent the 50 minutes that I was asked to go up to. So I'll stop there and take questions from the audience.
Thanks, Nick, for this interesting presentation. Like your videos are amazing, and your physical models are really great. And I'm sure that the students really enjoy it when they do this hands-on experience, right? I just want to ask you a question. You know how, like you're saying, that students prefer to do this physical hands-on activities, right? So, but what if there is like lockdown and they cannot do anything like on campus? Do you have any like solution or like anything that can be done? For example, as you said, there was some like windows of opportunities during, I think, one of the trimesters when they could actually go and do it on campus. What if there is no like such windows of opportunities? Is there like any other way we can better engage students, like other than videos and like other stuff? What do you think?
Yeah, you can. It is possible. One way of doing it, of course, is, I didn't mention this, but the Technolab system is portable. If I grab a frame here and just hold it up. put something behind it so you can see it a bit better against the background light.
Yeah, we can see it, yeah.
Oops. You can twist this round and push it in. You can twist that round and push it in so it's in plane. And you can place these inside a case, an aluminium case, so it's protected well. You can have foam between them. You can put the weights in there and you can send it out to a student or a group of 2 students if they're allowed to work and meet at home. That is possible.
Okay.
And if you have a class set of a dozen of these, as does Swinburne, next year they may consider, if the restrictions allow this sort of thing to happen, a pair of students to work together to be sent to their home. Of course, they have to be cleaned and all that sort of thing for COVID. And then it can be sent to another set of students over a period of time, short period of time.
Oh, I see. Yeah.
No, it doesn't have to be the Truss, because the frame can support a number of different experiments, and they're easy to introduce, to take these off and to introduce different experiments. So it really depends, like most things, on your finances. If you're prepared to support this activity and enable it, you need to purchase the equipment. One of the things I'd like dearly to see, and I suspect it's going to happen next year with either Swinburne and or the universities of Melbourne and maybe the University of Auckland, who have already purchased classroom bundles of my equipment, but for a limited number of experiments, that if they were prepared to augment those experiments with a simpler 2-bar truss, 4-bar truss, 5-bar truss, etc., they'd be able to build up and have something every week in their practice class tutorials that has a lesson to be learnt and make things easier for them to understand in terms of basic principles and way structures behave and operate. There are many smaller experiments. You could do more than one within a classroom setting. Some only take 2 or 3 minutes, but boy, the value of actually doing it yourself and seeing it for yourself and being able to play around with it yourself, that's got a lot of value to students. And in terms of cost, it's everyone asks, costs money. Yes, it does, but it's a lot less expensive. And I say that from experience because I'm competing against the bigger manufacturers who basically produce equipment not so much for hands-on as for demonstration. I'd like to see hands-on come back to universities, and by doing it well and providing a large range of options, it means individual lecturers and academics don't have to rediscover things for themselves and try and do it for themselves. It's there, it's available, they can use it. And boy, that saves a lot of time and a lot of expense because it's done well by a commercial entity that can supply to them and at an affordable cost.
Yeah, thanks, Nick. Are there any questions from the audience? Anybody would like to ask? Some people had to leave. I think they have some commitments. Anybody would like to ask? Well,
lunch.
Lunch. Can I just ask you then one more question before we finish? I think it's ready one time. So you showed those classes, right, where you use your equipment. So how many students in one class and how many pieces of this equipment do they typically use, per session?
Yeah, a typical set is a classroom bundle of 12 replicates.
Okay.
That's the frame and the experiment itself. Now, it can also work with 6 replicates if you need to, because you can have half the class working on the, if you like, the hands-on elements of that exercise, and the other half doing the theoretical modeling analysis side. And then you swap over, because most of the experiments can be done in minutes, and certainly if you built up to that experiment by doing the smaller experiments that involved similar features like photogrammetry and using the digital scales. If you've done that already, it's not a relearning exercise for you. You can do the Truss experiment well within half an hour.
Okay.
You can swap over and only buy 6 and have 2 students working on each and have a class of 24.
Yeah. Well, I think it's reasonable numbers, right? So, and I think students have enough time to play with this equipment. And
Yeah.
another thing, just you showed that Excel program, right? So did you write it by yourself and just did you give it to students, or like the students were asked to actually like do it by themselves?
They can do it by themselves.
They can do it by themselves.
They can.
That would be like a good experience for them if they do it by themselves.
It is.
Right?
It is. It's just writing down the simultaneous linear equations for each node.
Okay.
That's all I do. But having seen an example, and it's only for that particular case and that particular node numbering and that particular member numbering, right? You can give them the same exercise if you like, but with members numbered differently and nodes numbered differently. They can transform and do it, you know, if they want to be cunning about it. But if they're that smart that they can unravel what's there, they can do it from scratch, for goodness sake. So yeah, you can show them, here you go. You can get an answer for those member forces, and if they're not the same numbers as yours, yes, you can check against yours.
Yeah.
Look, I know that there's academics out there who believe that if you went to the trouble of programming the direct stiffness method for yourself, let's say for trusses, that you would better understand the direct stiffness method because you had to physically go through every step and program it. Well, you can do the same thing with my system. You can take a photograph of the entire truss and transform that to give you a rectified grid, because your photo may be at a slight angle or whatever. Apply the load and do it again. So before and after application of the load, you'll find out what the nodal movements are. Because you know the nodal movements, then you can break into the structure and look at each member individually. And from the capital XY displacements, you can convert it to member coordinates, rotation transformation. And then you can operate on the member coordinates to find out what the internal member forces are. Okay, and those steps can still be done and implemented, and as they are, in a direct stiffness method for trusses. And yes, you can still do the programming yourself, and you can learn a lot from that too. I'm not saying you won't, but boy, if you had the experimental evidence of it, then you trust a lot more the physics, if you like, and the fundamentals of equilibrium, the physics of what's going on. You can show that it works in real life, and real life being a physical model of a real structure, not a cartoon that has the transformations already done for it and solves the equations for you. I mean, that's what you're meant to be learning, to understand how that works, rather than have that to verify your solution. So yeah.
Well, thanks, Nick, for your presentation. I think we just
my pleasure.
Conclude here. I have recorded this presentation for those who couldn't attend, because we have several civil staff who are actually interested in your topic, but they were saying that, well, because we have like lectures and tutorials, like we're still in the middle of a trimester. So some of them just couldn't attend, but they asked me to record it. So I'm recording it and I finished recording it. So